the case study on regression. In this case study, we are going to take a problem that is on predicting price of pre-owned cars. So, let us go ahead and take a look at the problem statement. Now, Storm Motors, they are an e-commerce company and they act as mediators between parties who are interested in selling or buying pre-owned cars. Now, these are second hand cars and Storm Motors act as mediators. Now, in specific for the year 2015 to 2016, Storm Motors, they have recorded the data about the seller and car details. Now, these set of details include specification details, condition of the car, seller details, registration details, web advertisement details, make and model information and price. Now, these are several buckets and there are specific parameters or variables that Storm Motors has collected, and each of these variables will definitely fall into one of these buckets. Now, Storm Motors, what they want to do is that they want to develop an algorithm that will help them predict the price of the pre-owned cars, and this can be based on the various attributes that are associated with the car. So, let us see how to solve this case study in Python. So, let us start by importing a few required packages. First, we are going to import pandas for reading all the files from the CSV format. Then I am going to do a few numerical operation and hence I am going to import NumPy as well, and I am going to visualize the data and derive some insights, and I am going to import cborn for it. So, I am importing pandas as PD, NumPy as NP and cborn as SNS. So, let us just import these packages. So, these packages have been imported now. Now, I am setting the dimensions for all the plots that I am going to be generating. I am using the function sns.set. Set is a function from the cborn package, and within the parenthesis I am giving the figure size, and this sets the dimensions for our, and this will set the dimensions for all our plots. So, let us begin by importing the CSV file. So, you have been given a data called cars_sample.csv. Now, I have already set my working directory and the data is also residing in my working directory. So, I am just going to right away read it using the pd.read_csv function. So, the data has been read and you have 50,001 records and 19 columns. Let us just open and see what does the data have to say. So, you have index from 0 to 50,001. You have the date crawled, you have the name of the car, the seller type, the offer type, the price, you have A/B test, then vehicle type and year of registration, and there are a couple of other variables here. All these have been explained to you before, the description of the variables. So, now that we have read, let us just create a copy of it. So, you have already seen how to create a copy of your data. So, you can do a deep copy, and any change that you make to cars will not be reflected back in cars_data. So, I made a deep copy and I have saved it as cars, and we are going to be using cars to work hereafter. So, let us start by looking at the structure of the data. I am using the cars.info. So, this gives you the structure of the data. Now, this tells me that it is a data frame, it has entries ranging from 0 to 50,000 and the total number of columns are 19 here. What you also have is the number of non-null objects and what is the data type of each of the column. So, date crawled has 50,001 non-null object, it is an object data type. Similarly, you have name for seller type, offer type, price and A/B test, all these are full, and if you take vehicle type, that is 44,813 non-null entries. So, you have some missing values there, and similarly even in gearbox, model and fuel type. This will give you a gist of all the column names, and under each column the number of non-null entries and what is the data type of each of the columns. So, for us we have 6 columns which are of int64 data type, and there are 13 columns which are of object data type. So, now let us summarize the data. I am going to be using the function cars.describe for this. So, when I use cars.describe, you can see that there's a, so when I do a dot describe function, you can see the summary is given only for a few variables and it is not given for every variable. There are some dots that you see in between. Now, to get rid of this, you can use the, so when you do a summary, you can see the summary is given on, when you do a dot describe, you can see the description gives you the output in a scientific notation. What you also see is that it displays the summary of only a few variables and the remaining variables are displayed as dot dot dot. So, let us see how to get rid of the scientific notation first. I am going to use the function dot set underscore option. Within parentheses, what you have to give is display dot float format, because these are all float values and it is for these that we want to change the output. Now, there is a lambda function that we are declaring inside. So, what I am saying here is convert it to a 3 decimal place float value. So, let us just run this function again and then let us rerun cast dot describe. So, here you can see all the values have been rounded off to 3 decimal places, but we still are not able to get the description for all the columns. So, for that you need to use again the same function pd dot set underscore option. So, within parentheses you can give the parameter display dot max underscore columns and it will display the maximum number of columns, and the next parameter is basically how many ever columns you want it to be displayed. So, I have given a big number here 500, but usually you will not be seeing 500 columns in a data, but this is just to set the maximum number of columns that can be displayed. So, let us do that and let us rerun cast dot describe. So, now you can see that all your columns are displayed here and you have a summary for all of it. Now, price tells you that there are 50,000. So, under price, if you check the count, there are 50,001 records. So, all the records have been filled and the mean is about 6,559 and there is a huge standard deviation, it is about 85,818. The minimum value is 0, the first quartile value is 1150, the second quartile, which is also the median, is 2950, the third quartile is 7190, but the maximum is very huge. And if you look at the difference between the mean and the median, which is the second quartile, you can see there is a huge difference between the mean and the median. This itself shows you that price is very skewed. And if you take year of registration, you have 50,001 non-null values. The mean of year of registration is 2005, but this does not make sense because year of registration is an integer and it cannot be rounded off to a decimal. But if you take the minimum of it, you can see there are years ranging from 1000. Similarly, if you look at Power PS, it again has 50,001 non-null values, the mean being around 117, and if you look at the median, the mean being around 117, but if you look at the minimum value, the minimum is 0, which does not make sense again, and the first quartile is at around 70, the second quartile, which is the median, is around 105, and the maximum is very high, the maximum is around 19,312 horsepower. Now, then you have kilometer has again 50,001 non-null entries, its mean is about 1,025,613 kilometers, the minimum is again 5,000, the maximum being 1,50,000. Next you have month of registration. Month of registration does not have any missing values. The minimum again is 0, but 0 does not make sense, and postal code is something that we will be getting rid of because we are not going to be using for this case study, but you are free to use this variable if you want to do a more spatial based analysis. Right. So, again even for postal code they are all integers and you cannot have decimal values. So, let us just start by dropping unwanted columns up front. Now, you have variables like name, date crawl, date created, postal code and last seen. Now, we are not going to be using these variables for our analysis and I am going to just drop them. So, I am creating a list of all the variable names here, and once I run it, all of them are stored under call, and I am just going to use the dot drop function and to drop them. So, I do a cast dot drop and I say columns is equal to call. So, these are the columns I want to drop. Since these are columns, I am giving the axis as 1. So, from 19 you can see the number of columns have come to 14, I have dropped 5 columns here. Now, we are going to see if there are any duplicate records in our data. right, and if there are any duplicate records, we are just going to keep the first occurrence of that such records. So, we started out with 50,001 records. Let us see, when you do a dot drop underscore duplicates, how many are we losing. So, from 50,001 it has come down to 49,531. Now that we have removed it, let us get into data cleaning now. So, my first task is to compute the number of missing values under each column. Now, from the dot info function we saw not all columns were filled, right. So, now we are going to find the number of missing values under each column, and later on we will come up with a method of how to logically fill such missing values. So, the first step is to basically calculate the number of missing values under each column. So, I am using the isNull function. So, isNull will basically return a data which is true or false. It will mark the cells which are missing with true, but I am going to sum up the occurrences of the trues. So, I am just going to do a dot sum for it. So, if you run the function, you can see on my right that seller of a type price AB test do not have any missing values. Now, vehicle type has 5,152 missing values. Year of registration is again full. Gearbox, however, has 2,765 records missing, and under model you can see you have about 2,730 records missing, and under fuel you can see you have about 4,467 records missing, and about 9,640 records are missing and not repaired or damaged. So, this is the column wise count of the number of cells that are missing. So, now let us just take year of registration first. So, in line 75 what I am trying to do is I am trying to find a year wise count based on this variable. Now, you can use the dot value underscore counts here, and I am sorting the index to make sure that the year of registration is sorted based on the years and not on the counts. So, by default if you do a dot value underscore counts, you would have seen that. So, it gives you the category with the highest frequency on top, but I do not want that. I basically want it sorted based on the years. So, let us just run this. This is too big output, so I am saving it on to year wise under count variable. Now, if you open and see, so let us just see what this data frame has. It has index and it has year of registration. Index is the set of all years, and year of registration under that column you basically have the frequencies of each of these years. So, you have years that are ranging from 1000, and then you have year from 1910, and what you can also see if you scroll down is that you have years which are in the future, that is which are after 2019. So, most of these do not make sense. So, there is considerable amount of cleaning that we will have to do for this column. So, let us see how to come up with a strategy to clean them. So, if you look at the sum of records which are greater than 2018, then that is only 26, right. This is too less a number and we cannot predict in the future. We are in 2019, but I am not considering that because it has occurred only twice and it would not make sense to consider it. So, if you look at the number of cars where registration is greater than 2018, now you have about 26 of them, 26 records have a year that is greater than 2018. Now, similarly, if you do for a lower end check, what you can also see is I am taking the limit 1950. So, if you look at the cars that are made before or that are registered before 1950, then you have about 38 records of that kind, right. Now, these are too less, correct, and they are going to smear or affect or sway the effect of the model. So, we are going to get rid of them. So, the working range that I am going to set is between 1950 and 2018. So, just to reconfirm this, if you do a scatter plot, I am using the SNS.rig plot. If you look at the scatter plot, I have the year of registration on x axis and I have the price on the y axis. Let me just drag it to the side just to show you a better plot. So, you can see that the plot is not explaining anything, you have only dots here and there, and that is because there are values which are very high and they are just smearing out the effect on the other points. So, we have to clean this column to really understand what is the effect of year of registration on price. So, that is as far as year of registration goes. The next is the variable price. Now, if you again do a dot value counts and then you sort based on the ascending order of the price, and I am just saving it on to the variable price underscore count. So, the left is basically the index and that is the value of the price of the car, and the right is basically the frequencies of each occurrence. Now, that is too huge a range. So, we have to tweak it down, and even price equal to 0 will not make any sense. I mean, it can be, because if you want to just sell it for a few dollars or a few for a very low amount, you can, but then we are looking to generalize this model for a workable range of data, and these values can be very very extreme, right. So, there is nothing wrong in selling a car for a lower price, but then we would like to generalize a model that would come up with a better prediction, but however, these if you have these values, then they are going to smear the effect out. So, we are going to do a check on this as well, and we are going to arrive at a working range that is easy for us to understand, right. So, now if you do a histogram which is using the dist plot, right, you can see that because there are a lot of entries under the 0 price category. So, this is something that we have to work on. So, let us just quickly reiterate it by even looking at the describe. So, describe also tells you that the mean is about 6,567, the median is way off, the median is around 2,950. Now, there is a huge difference, and this itself accounts for the skewness in the data, and the minimum here you can see is again 0 and the maximum value is also given. So, the range is really wide, and we have to narrow it down to come up with a generalized model. So, let us just quickly do a box plot. Now, a box plot also tells you that there are some outliers here, right. If I do a box plot for the price, you can see you can't even see the box, in fact, what you just see is a line. Now, this itself tells you that there are considerable outliers in your data which are very extreme in nature, and hence you are not able to really see the behavior of the variable. So, let us just do a quick check of the range. So, I am setting the range between 100 to $1,50,000. So, the first is to see how many cars are priced above $1,50,000, and that is about 34, and if you do a price check on the lower end, you will see that 1,748 cars are priced lower than 100, but this is okay because $100 to $1,50,000 is a decent range to work with. So, the next variable that we are going to look into is power PS. Now, again if you do a dot values counts and then you sort it, and I have saved it under power count. So, here again you will see that the power values are on the extreme left, and the right hand side is the frequencies of each. So, 5,533 records have a power 0. Again we have the same problem because the range is too diverse, and we can't really infer much. So, we have to again narrow it down. Somewhere in between you have a lot of occurrences of ones, some of them are too extreme. For instance, you have 19,312 horsepower, that is very extreme, and it has occurred only once, and so we have to narrow down the range of power PS as well. So, let us just do a dist plot just to see if there is any skewness. Yes, there is. You can see that from here itself, because of entries that are of 0. So, this is something that we have to take into account, we have to clean it up, and if you do a dot describe, this will also show you the skewness. We have already done this before, just reiterating it here. So, the mean is about 116, and if you look at the minimum it is 0, and if you look at the first quartile it is around 60, it is around 69, and if you look at the median, that is around 105. Though the mean and median are not far away, the standard deviation is quite huge. Now, for a mean value of 116, if you are going to deviate by around 200 units, then that is a lot, right. So, though the mean and the median are not very far, but they are still far, there is still some skewness, but if you look at the range of power PS, it is too diverse, and you also have values that are around 0. So, you just even if your mean and median are very close, you also have to take into account the standard deviation in the data, and in this case it is very huge, right. So, we are going to take up this, we are going to tweak the range down, but before we do that, let us just quickly see if this is also getting reflected in the box plot. This plot is a lot better compared to the price plot that we earlier did. There we were just able to see a line, at least here you are able to see a small box. So, yes, of course, you have some extreme values here that are actually compressing the box. So, we will have to deal with this, and we have to come with a workable range of data. So, let us just plot and see if power PS has an effect on price before we clean it up. Again, it is all bundled up together on the lower end, and I think that is because of the values that are 0. We have to clean it up before we further do anything with this variable, because otherwise we will not be able to see the effect of this variable on price. So, let us just fix a range. So, I am fixing a range between 10 and 500. Now, I have arrived at all these ranges by trial and error. Also, the idea is that you do not want to let go of too many records, correct. So, I am going to check the number of cars that have a power PS of greater than 500, and that is about 115, and if you take the lower range and if you take the lower value, the number of cars that are less than 10, it is about 5565. These are from trial and error, and there is considerable reading that has been done to even check what is the minimum power that you need to start any vehicle. So, the working range for year of registration is between 19 to 50. The working range for year of registration is between 1950 to 2018, and for price we are sticking to 100 to $1,50,000, and the working range for power PES variable is from 10 to 500. So, now that we have checked the working range for 3 variables, we are now going to clean the data by giving these variables, and any further modifications we are going to do in the clean data.